Shahir, and I'll tell you about our paper titled Bi-parametric prostate MR image synthesis using pathology and sequence conditioned stable diffusion. So let's first start with what is stable diffusion-based image synthesis. Well, diffusion or stable diffusion is a newly proposed conditional image synthesis method that can accommodate complicated conditions, for example, long text prompts. So it can generate images based on those complicated conditions. As the authors for the original image synthesis using diffusion papers say, that it was called diffusion because it was inspired by considerations from non-equilibrium thermodynamics. And what that means essentially is that it gradually adds noise to data in a Markov chain, and the model learns to reverse this, so to reverse the noise addition process. These kinds of models, the ones that you might have heard of, like Stable Diffusion, DALI, or the likes, like Imagen, they are trained with billions of image text pairs from the web. So you have an image, and the condition that it's conditioned on is the text that corresponds to that image. So that was an overview of what stable diffusion or diffusion-based image synthesis looks like. But the main competitor or predecessor to these models for image synthesis was generative adversarial networks, and there are some inspirations in diffusion models from these kinds of generative adversarial networks. So next we'll take a look at that. Generative adversarial networks, or GANs, consist of two functions, the generator and the discriminator. Noise goes into the generator, which produces a fake image, which is then fed into the discriminator, which can tell if the image is real or fake, or how real or fake the image is. Realism prediction by the discriminator also serves as a supervision signal for training both of those functions, so training the generator as well as for training the discriminator. So in GANs, we try to directly go from noise to the original image or to a sample, which is intuitively a very difficult task to go from noise to the image in just one step. So GANs have a tendency to suffer from problems such as mode collapse, for example, creating the same image every time, or diminishing gradients, which are difficulties during training and things like that. So that was an overview of GANs, and now for diffusion models, they work based on sequentially added small amounts of noise rather than trying to go directly from a noise sample to an image sample, which is intuitively an easier task compared to GANs, which try to directly go from noise to the image. But these diffusion models are slower to train because of this iterative nature, so you add small amounts of noise and you learn to reverse that small amount of noise addition process. So essentially we want to learn a function that goes from the last noised image to the first one, which means that we want to reverse that noise addition process. We have paired data for noise to image, but learning this task is too difficult, and GANs do attempt this. So we only learn to remove some noise given the time step. So we learn to remove noise at every time step in this sequential noise addition process. Stable diffusion is also more strongly conditioned on conditioning variables. For example, text prompts, due to something called classifier-free guidance, where it's depicted in the image on the bottom here, where you input a condition into the network, and you have your noised image, and you subtract the condition output from the output which was generated without any condition. So that's how you have classifier-free guidance, where you subtract those two with the condition and without the condition, and then you maximize the difference between the two. So our proposed method basically proposes to condition the diffusion model on images as well as the conventional text prompts to control the MR sequence and also the presence of prostate cancer respectively for those two things. So in our experiments, we have a diffusion model that is conditioned on the MR sequence, lesion presence, so prostate cancer lesion presence, and the images for paired biparametric MR image synthesis. And so here we have training data of around 8,000 2D samples of MR, and based on this training, we then have a few quantitative results to share, which are, firstly, we tested an expert clinician versus, and to see if they can identify real versus fake samples over 64 different images, and they got an accuracy of 0.59, where chance is only 0.5, so it's quite close to chance. Second, the lesion identification accuracy as performed by the expert was 0.6 for real images and 0.63 for synthesized images. So again, that's very close, which tells us that the distribution of synthesized images is quite close to the real images. Lastly, we trained a machine learning model, first with real data only, and then with synthesized data plus that original real data. And we got a 5.8% accuracy improvement when we trained with the real data augmented with synthesized data compared to only real. And then at the bottom here, there are some qualitative results presented, where green are the real samples, blue are the fake ones. And then the left part shows no lesion, and the right part shows a lesion, where there are some small arrows indicating where the lesion is. And then the top, middle, and bottom plots are the modalities, as well as the bottom one is a paired synthesis between T2 and DW. So we feed in the T2 weighted image and get output of the DW or diffusion weighted image. So to conclude, we present a stable diffusion-based image synthesis method together with a conditioning scheme to generate realistic prostate MR images. The sequence of MR, presence of lesions, and synthesis of paired data may be controlled using those conditioning variables that are allowed in stable diffusion. And then quantitative results demonstrate that the usability of the generated images for use cases such as training or for improving machine learning model performance is demonstrated in the paper. And that brings us to the end. Thank you very much for listening.